Hello, everyone. Hello again. Today's topic is elastic potential energy and oscillations. So the first problem that we're going to do is simple harmonic motion. So the differential equation of simple harmonic motion is this, is the second derivative is equal to uh, minus omega squared times x. So the first problem is to verify that this is a solution of this differential equation. What does that mean? Well, look, if we take x, x is the position of a body. X dash, which is the derivative of the position with respect to speed. So change in position divided by change of time. Can somebody help me? If you divide change in position by change in time, what do you get? Yeah, you get velocity. V is velocity. And if you differentiate velocity, that is dv dt, is the change in velocity divided by change in time. That is acceleration. Yes, acceleration. And it's the derivative of v, but v is x dash, so it is x double dash. Now, when we are talking about the derivative with respect to time, we can replace the dash with a dot. So x dot means x dash or dx dt. So these are the same thing. These are equivalent. Just a convenient way of writing. So if you write x double dot, everybody understands that it's the second derivative with respect to time. So this equation can be rewritten as x double dot is equal to minus omega squared x. So the second derivative of x is minus omega squared times x. And this is called a differential equation. We don't do differential equations exactly in this course, in the year 11 course, but we do them in the year 12 and year 13. Now, a differential equation is an equation which contains derivatives, as simple as that. And the solution to a differential equation is a function. Okay? So, for example, y double dash is minus 9y. So this is a differential equation. Why is it a differential equation? Because it contains a derivative. And I will attempt to guess a solution. I want to guess what y is. Okay? And my guess is going to be y is sine 3x. Okay? So this is my guess. Just a second. Of course, it's not a random guess. Okay, so I'm going to differentiate that. I'm going to find the derivative of sine 3x. And we know using the chain rule, it's 3 multiplied by cosine 3x. And if we differentiate that again, it's going to be, well, it's going to be minus 9 sine 3x. But wait a minute, wasn't sine 3x just y? If we use that, then we can say that y double dash is minus 9y. So y equals sine 3x is a solution. Is a solution because I substituted it in and I verified that, well, it's true. Y double dash is minus 9 times y. Do you understand what I've done on a scale of 0 to 10? Can you let me know? Do you understand conceptually what I have done? So do you understand that this is an equation and this is the solution? This is the equation and this is the solution. On what basis did I do a guess? It's complicated. um, this is something. This is something beyond this course. On what basis I'm making the guess? It's just sometimes you can easily guess. Like for example, this differential equation: y dash is 3. Well, that's an easy guess because y is simply 3x, right? Well, it's 3x plus c technically. You just differentiate. You could integrate both sides. Yeah, let's see if I could integrate. Y double dash is equal to minus 9y. If you integrate that, well, not really, because when I integrate the right-hand side, I get the integral of y, which is y. What would I get? It's just the thing is, if I integrate twice, I must get minus. No, that doesn't really work. Uh, if I integrate it twice, I must get a ninth of what I had initially. So y is minus 1/9 of y double dash. So I know that the cosine, when you differentiate a cosine twice, you get cosine, and that's the basis of my guess. Yeah, because when cosine x is differentiated twice, you get minus cosine x. That was the reason for my guess. Okay, I hope that makes sense. Now here, they're saying show that x is b, where b is a constant, sine omega t plus alpha, where alpha is an arbitrary constant. Show that is a solution to x double dash double dot is minus omega squared x. That's what we're trying to do, right? So this is the gist of the problem. Let's do that. So what I'm going to do, I'm just finding x, x is b sine omega t plus alpha. Now using the chain rule, I just differentiate. I differentiate x, so it's going to be b multiplied by cosine omega t plus alpha multiplied by the derivative of that, omega t plus alpha dash. But the derivative of that is simply omega because we're differentiating with respect to time. So it's going to be b omega cosine omega t plus alpha. Now I differentiated twice. I differentiated for the second time, and I get b multiplied by omega is a constant. Then I multiplied by minus sine. So the derivative of cosine is minus sine omega t plus alpha, and multiplied by omega t plus alpha dash, which incidentally is omega. So it's minus b omega squared sine omega t plus alpha. And if I substitute that into x double dot equals minus omega squared x, I get minus b omega squared. So x double dot is that, right? So this goes in here. Minus b omega squared sine omega t plus alpha equal minus omega squared multiplied by x, and x is b sine omega t plus alpha. Wow! Isn't that just beautiful? Because sines cancel, omegas cancel, minus cancels, and b cancels. We just get 1 equals 1, which is true. True. So that means that it is a solution. So x equals b sine omega t plus alpha is a solution. Where b b and alpha are arbitrary, very constant. So they can be anything. I'm pretty sure they can even. No, let's not go there. They're arbitrary constants. Okay, so that's that. Uh, okay. So I'm going to take this. One equals 4. Okay, so for the second problem, we have a graph, and we have a graph, and from the graph, we need to estimate the amplitude of the oscillation. Okay, so the amplitude of the oscillation is, well, here it's 4. Amplitude is 4 because it goes from 0 to 4 and then to minus 4. The period, well, to find the period, we can go from, well, let's say from here. There's 1, 2, 3, 4 periods, and this is 1. So this is 0.8, and this is 8, 9, 9.5, 9.25. So the period is 9.25 minus 0.8 divided by 1, 2, 3, 4, 4. So period is approximately this, and 9.25 minus 0.8 divided by 4. So that's 9. No, it's not. Divided by 4. 2.11. Okay. Well, seconds, assuming that this is time. To a period, that's the period. The frequency. Well, the frequency is simply 1 divided by period. And that's equal to 1 divided by 2.11, which is approximately is 0.4733 hertz. The angular frequency, that's 2 pi f. So 2 pi multiplied by f. So frequency is f. Angular frequency is omega. Period is t. Amplitude is A capital. Angular frequency 2 pi f. So multiplied by 2 pi gives 2.97. 2.97 radians per second, which is technically the same as hertz, but we keep it 2.97 radians per second. The phase. Now, the phase is the hardest part. Phase. So the phase is that number. So if this equation, this is a sine graph. So this is x is equal to a multiplied by sine omega t plus phi. And to find phi, phi is the phase. So we substitute t equals 0. Sub t equals 0. We know that the amplitude is 4. So, and x at 0 is -3. -3 is equal to 4 multiplied by sine omega times 0 plus phi. Or in other words, sine phi is minus 3/4. So phi is approximately minus arc sine of 3/4, which is, well, we can do it in radians. Arc sine of 0.75, 0.848. This is the initial phase. Phase is phi equals 0.848. So now we can deduce the equation. Equation is x is equal to 4 multiplied by sine omega t. So omega is 2.97 t plus 0.848. That is the approximate equation. Approximate equation. And let's look at the true equation. And the true equation is this. This is what I put in the calculator. True equation. True equation. Equation. Well, it's not y, of course. It's x. It's x, and this is t. But you can see that 2.97 is approximately 3. 4 matches. And 0.848, oh, so minus is 0.848, which is approximately pi over 3. So this is approximately this. So not bad. Not bad. So should I say a few words about phase? Or do you think you understand phase? Okay. Phase represents where you start the oscillation. Okay. So imagine you have a child on a swing. What can you do? Well, you can pull the child back and release, or you can push the child forward and then release, or you can, well, push the child at the lowest position, just push really hard, and the child flies forward. Or identically, you can push the child backwards. So, yes. Or you can pull the child a quarter way up, well, halfway up, and then push. So, depending on how you start your oscillation, that's what we call phase. Right. So, uh, so what is phase? X. So let's say X, sorry, that's T time. X is the amplitude multiplied by sine omega t plus phi, right? Uh, so if you push the child at the lowest position, the child will go like this. So this is push at lowest position. That means at t equals 0, the child is at the lowest point. So you just push. What are the units of phase? It's a non-unit quantity. Well, it's radians, but radians is a non-physical quantity. It's not, doesn't have a unit of measurement. Unitless quantity. What is phase? So this is, we say phase is 0. If you pull the child backwards, that means the child starts from the uh, uh, minimum position. Minimum means furthest backwards. Furthest backwards. So, and then you release the child, and then the oscillation will go like this. Release the child from the furthest back position. And in this case, phase is going to be -1, so minus pi over 2. Okay? Because if you substitute minus pi over 2, so x is a, so this is minus a, and this is a. So this is a swing, and the swing goes left and right. This is the extreme position. So this is 0. This is the plus a, and this is minus a. So the chart goes between minus a and a, right? So it's the left extreme, right extreme, right? So it's a forward. This is forward, forward, back. So if you start from this point, this is phase. Phase is a minus pi over 2. If you start from here, phase is 0. And if you start from here, phase is similarly pi over 2. So if you start the chart from the furthest forward position, and let's see how that looks like. It looks like this, right? So release at maximum position. And that means phi is pi over 2. And if you release the child from the lowest position, from the center, but going backwards, so that's the fourth possibility. There's infinitely many possibilities, of course, but the four simple possibilities. push at lowest position, but backwards. In this case, phase is pi, or minus pi for that matter. It doesn't really matter. Okay. So I hope that makes sense. Let's see how that looks on Desmos. Um, okay, so I'm going to put 2x plus sine x minus plus alpha. And we can add a slider alpha. So you can see that as we change alpha is the phase, as we change it, the starting position of the child changes. So here, the child starts at position 1. Yeah. Here the child starts at the highest position. And this child starts at the lowest position. Lowest means the furthest back. And here it starts from the center. This 6.3 starts from the center. So that's what phase does. Does that make sense about phase? Let me know in the chat, please. Okay. Right. And yes, it is recording. Lovely. Next question. The phase, well, usually we say the phase is between 0 and 2 pi, but it can, there's no real limit. Like, honestly, you can say minus pi over 2, which is the same as 3 pi over 2. So minus pi over 2 or 3 pi over 2. So it doesn't really matter. I normally say phase, typically the phase is either between minus pi and pi, or the phase is between 0 and 2 pi, like this. So including 0, not including 2 pi. Right, but this is not a strict, strict. Okay. A shadow from circular motion. So if you think of a wheel rotating, and you take just the y coordinate. So imagine you have a point on a wheel, and as it goes around and round, that point P, it goes up and down. So if you look from the side, you will see that the point P goes up and down. So it goes up and down. Point P just oscillates. All right, so in the y coordinate of point P, y coordinate of point P oscillates up and down. Okay, so wheel radius 1.5 meters, 0.5 meters, and 2 revolutions per second. So that's frequency is 2 hertz. Write an equation describing the horizontal position. Oh, sorry, horizontal position of the point, of the point's shadow on the wall as a function of time. Sorry. Well, we just shine some light from the side, and the horizontal coordinate, point P. Um, Actually, you know what? I think we can. So, circular motion, circulation versus oscillations, uh, animation, animation. So here is a ball rotating. You can see that the shadow of the rotating ball behaves exactly the same way as the shadow of the oscillating ball. I I love this demo. Okay. Yeah, so that's what's going on. And so this ball, we assume it makes 2 rotations per second. Frequency is 2 Hertz. And we want to know the equation. Well, except you can assume that we're shining light from the top and the shadows on the floor. So let's rotate this image. See if we can get somewhere. If we rotate this image. So like this. Okay. And you can see that the shadow goes oscillates. This is the center. The shadow oscillates back and forth. Okay, now um, we can remember the we can remember the trigonometry, right? From I think we've done that in year 10. So this is radius, and this is the y coordinate. This is the x coordinate. And if you write like this, like this is the radius, and this point has coordinates x and y. And if this angle is theta, let's say it rotates in the other direction, simplicity. So it rotates in that direction. So this angle theta, and if you take that, then this is a right angle triangle, and this side is equal to, well, r cos theta, and this side is equal to r sine theta. But also that's equal to y and that's equal to x. So in other words, x, the x coordinate of point P is r cos theta. Now, what is theta? Well, theta is the angle it turns through. And by definition of angular velocity, angular velocity is the angle divided by time, is the change of angle divided by change in time. So in other words, angle divided by time. So theta is omega multiplied by t. And we can substitute that in. So x becomes r multiplied by cos omega t. Ooh, doesn't that look familiar? Doesn't that look like the equation of simple harmonic motion? Whereas where r is the amplitude and phase is 0. Yes, compare compared to x is equal to a cos omega t plus phi. So where the starting phase is 0 and a is the radius of the circle. That is a beautiful result, and it does prove that. Yeah, so now we just need omega. Well, omega, as we know, is 2 pi multiplied by the frequency, so it's 4 pi. And the radius is 1.5 meters. Therefore, x is equal to 1.5 multiplied by cosine 4 pi t. That is the equation of motion, and that is in meters. That's the position of the shadow in meters from the center of the oscillation. Okay. Position in meters. Lovely. All right, so moving on. Oscillatory motion from rotary motion. An electric motor rotates at 30 Hertz and drives a piston using a Scotch yoke mechanism. Okay, so Scotch yoke mechanism. And that looks like this. Scotch yoke. So this wheel rotates. The wheel rotates, and as it rotates, this knob rotates, and that purple thingy moves left and right with the ball. So the horizontal position, the x position of the purple thingy, is equal to the horizontal position of this knob on the on here. Let's see. Can I watch that? This is how it looks like. Okay. Electric motor rotates at 30 Hertz and drives a piston using a Scotch yoke mechanism. The radius of the rotating arm is 4 centimeters. So the radius is 4 centimeters. And the frequency is 30 Hertz. And estimate the maximum speed of the piston. Well, maximum speed of the piston is the maximum horizontal speed. And we know that x from the previous problem, we know that x is the radius multiplied by cosine of omega t. So omega is 2 pi f. So that's, well, that doesn't matter, 2 pi f. Now, we know that the velocity is the derivative of x. So that's equal to r multiplied by omega multiplied by sine omega t, well, with a minus. So V is maximum when sine omega t is -1 because, well, because it's a minus. So V max, as you can see, is R times omega. Oh, beautiful result. So we just need radius, which is 4 centimeters, multiplied by omega, which is 2 pi multiplied by f, which is 30 Hertz. And that gives us 4 times 2 pi times 30, 240 pi, so 754 centimeters per second, or it's 7.54 meters per second. That's the maximum. That's the top speed. Lovely. Okay, moving on. Mhm. Energy in simple harmonic motion. A mass undergoes harmonic motion with displacement. Expression for the kinetic energy and potential energy as functions of time. Okay. Um, so we know that the kinetic energy is 1/2 m multiplied by v squared. And v, velocity, is the derivative of displacement. So let's calculate the derivative of displacement, and that's equal to a minus a omega multiplied by sine omega t. Okay. And then I can square that. So v squared is a squared omega squared multiplied by sine squared omega t. Okay. So kinetic energy is equal to 1/2 multiplied by m multiplied by a squared omega squared sine squared omega t. Kind of a lot to take in. Right. Now, potential energy. It's very difficult to find the potential energy because, well, potential energy depends on the relative position. If it was a spring, it's easy. Potential energy is 1/2 kx squared. But this is not necessarily a spring. So let's try to solve it for the general case. Um, Kind of beats the purpose of the problem. Uh, and we're not going to do question 3. We're going to use question 3 to solve problem 1 because, well, yeah, it's because it's difficult to talk about potential energy. Like, how do you do potential energy without knowing what the system is? All right. So potential energy plus kinetic energy is constant because that's called the total energy. That's the total energy. Therefore, we want to know how much total energy there is. So imagine an oscillating system. Imagine a pendulum that goes swingity swing, right? At the top position, the kinetic energy is 0, but the potential energy is maximum. So in this position, identically, kinetic energy is 0, potential energy is maximum. But at the lowest position, potential energy is 0 and kinetic energy is maximum. But as we know, the total energy is fixed. We can safely say that the kinetic energy at the bottom is equal to the potential energy at the top. In other words, the total energy is equal to maximum kinetic energy. And because kinetic energy depends on includes sign, so this is a constant value, and the sign takes values between -1 and 1. So the maximum kinetic energy the maximum kinetic energy is 1/2 m a squared omega squared without the sign, right? Because sign has to be 1. Sign equals to 1. Uh, and that's really cool because now we can rewrite that equation. So total energy is equal to potential energy plus kinetic energy. And total energy is 1/2 m a squared omega squared. Potential energy is what we're looking for, plus kinetic energy is 1/2 m a squared omega squared sine squared omega t. And now making potential energy the subject and taking out everything out, 1/2 m a squared omega squared, open bracket, 1 minus sine squared omega t. And 1 minus sine squared omega t is obviously cosine squared omega t. So it's 1/2 m a squared omega squared cosine squared omega t. But that is a beautiful result. So let's just admire this. So the kinetic energy of an oscillating object is 1/2 m a squared omega squared sine squared omega t, whereas the potential energy is 1/2 m a squared omega squared cosine squared omega t. And if you add them all together, you get the total energy, which is this plus that, and sine squared plus cosine squared is just simply 1. So you just get 1/2 m a squared omega squared. Right, total energy. Um, let's see that in action. And let's do a Fed energy circus. Oh no. Energy skate park. This is as close to an oscillation as we can get. And look at the energy. Kinetic energy decreases, but the total energy remains constant. Okay. Yeah, so we need to adjust the reference height. So you can see that kinetic goes to 0, maximum, maximum, 0, maximum, 0, etc. Okay, so this is the idea about energy, and yeah, and it has a beautiful result. But we can go a step further. But remember that x, the position, was a cosine omega t, wasn't it? A cosine omega t, yes. So x squared is a squared cosine squared omega t. So if we take this equation, for the potential energy potential energy is equal to 1/2 m omega squared x squared. It's a very useful thing. And we could also say that, well, sine a squared sine squared omega t is the same as a uh, squared 1 minus cosine squared omega t, which is a squared minus a squared cos squared omega t, which is a squared minus x squared. Therefore, the kinetic energy can also be rewritten in terms of x, in terms of the position of the object, is equal to 1/2 m omega squared a squared minus x squared. And the total energy is adding these two together, which, if you are observant enough, you will see that it is 1/2 m omega squared a squared, the same expression as we had before. Okay. And now, for a cherry on the cake, if you've still kept with me, if we compare to our kinetic energy equals to 1/2 mv squared, you can see that this is 1/2 m times something squared. So v squared is omega squared a squared minus x squared, or the velocity is plus or minus omega square root a squared minus x squared. This is another very useful formula. Yeah. Okay. So that's that. Sketch both energies. Sketch both energies over one time period. Oh, that's very useful. Okay. So we have energy versus time. So this is time, and this is kinetic energy. Well, kinetic energy is 1/2 ma sine. So kinetic energy goes like this. So time period. So it goes like this. So this is time period over 2. This is time period. So this is kinetic energy is equal to 1/2 ma squared omega squared sine squared omega t. And now cosine starts from here. So this is the maximum value, 1/2 ma squared omega squared. And this is the potential energy. Potential energy is 1/2 m a squared omega squared cosine squared omega t. And if you add them together, you get the total energy, and the total energy is just this horizontal. The total energy is just this horizontal line. Total energy is equal to 1/2 ma squared omega squared. So that's energy versus time. This is energy versus time, and it's also useful to draw energy versus x. So the energy versus x is the position. And you can see that the potential energy is a quadratic function of x. So potential energy potential energy is proportional to x squared. So it looks like a parabola. Okay. So this is the maximum displacement. So this plus A, and this is minus A. And this is the maximum energy, which is 1/2 m omega squared A squared. And that's the potential energy. Now we're using a blue color for kinetic energy. Oh no, red. Red color for kinetic energy. And kinetic energy is 1/2 a squared minus x squared. So here it's maximum, and here it's just 0. So that's like this. So that's the kinetic energy. Kinetic energy, which is equal to 1/2 m omega squared a squared minus x squared, if you draw the graph. And the total energy is a horizontal line. Total energy. Total energy, which is quite interesting in my world, of course. Okay. All right. A small projectile, mass m, moving horizontally with speed v, embeds itself in a stationary block of mass m attached to a horizontal spring of stiffness k. So we have a ball and a spring, stiffness k. There's a frictionless ground force. Okay. So a small projectile, so mass m, and the big mass, so it's traveling with speed v, embeds itself in a stationary block m and they start moving off together. So first we need conservation of momentum. Conservation of momentum. Momentum. So mass 1 times the initial velocity 1 plus mass 2 times the initial velocity 2 is mass 1 times the final velocity 1 plus mass 2 final velocity 2. That's conservation of momentum. And we know that the initial mass m times v plus 0, because that mass is stationary, equals mass 1 times, let's say it's moving with the velocity u after the collision, m times u plus m capital times u. And here we can find, so u, the initial velocity of the mass, is m divided by m plus m times v. Okay, so that's the initial velocity of the mass after collision. So once they collided, they start moving off at velocity u. So now what we have is we have a mass of m plus m. So it's a combined mass attached to a spring with spring constant k and moving with velocity u. And this is past the equilibrium position. Equilibrium position. Right. So for a mass spring system, so if you move the mass by a distance, if you move the mass by a distance x, so if this is the x-axis, this is 0, and this is plus x, the force that will result would be minus kx. So the force in the spring is minus kx, and mass, we know, mass is m times acceleration. Mass times acceleration. Well, in this case, it's m plus m times acceleration is equal to minus kx. And acceleration is minus k over m plus m x. Compare this to a equals minus omega squared x, because that's the equation of simple harmonic motion. And here, if you compare these two equations, you can see that omega squared is k over m plus m. In other words, omega is square root of k over m plus m. That's the angular velocity. And what else do we need? We need the initial phase. So, oh, we need the amplitude. Ooh, to find the amplitude. We know that V max is amplitude multiplied by omega. This comes from the equation of simple harmonic motion. Amplitude times omega, and that means that the amplitude is omega divided by V max, which is square root of k over m plus m over V max. But the maximum velocity is the initial velocity because it starts with the maximum velocity divided by u, which is square root of k over m plus m, divided by u, which is m divided by m plus m times v, which is square root of k square root of m plus m divided by mv. If that's, I don't know if that's helpful. K m plus m over mv. Okay, that's the amplitude. Um, and we need the initial phase. Right. So, equation of simple harmonic motion is x equals a sine omega t plus phi. And we know that when t is 0, x is also 0. That means 0 equals amplitude multiplied by sine 0 plus phi. That means sine phi is 0. So phi is 0, or phi equals pi. Almost phi equals pi is, remember, it's starting from the 0 position, but backwards. So, but we know that we're going forwards, so we just choose this one. So phi is 0. So finally, the equation, the answer. X of t, because x is a function of t, is the amplitude, which is the square root of k m plus m over mv, multiplied by sine omega t, and omega is square root of k over m plus m multiplied by t. And that is the solution. That is the equation. Okay, this is the equation of motion of the big mass once the small mass gets embedded inside. Okay, okay. The next one Effect of changing a spring configuration. A mass oscillates on a vertically on a uniform elastic cord. So we have an elastic cord, and there's a mass, and it oscillates up and down. Okay. Now it's the spring constant. Well, we can assume that there's a spring constant K. Describe how the frequency changes if the cord is folded exactly in half and attached so that both strands share the load equally. So effectively, we now have two cords of half the length and a mass attached to it. Okay. We also know from the previous result that omega squared. Well, let's actually, you know what? Let's do it over again because it's very useful, right? So if you have a spring constant K and a mass M, if you move the mass, and this is 0, this is the x-axis. So you move the mass slightly to the right, a distance x to the right, plus x to the right, and there will be a force to the left. So the force is minus kx. Because if you move the ball to the right by x, there will be a force to the left, which is equal to minus kx, because that's Hooke's law. And we can rewrite that. We can say that F is equal to minus kx, but F is equals ma, but F is ma. So ma equals minus kx. Divide both sides by m, so a is minus k over mx. Compare to the equation of simple harmonic motion is a minus omega squared x, and we can see that omega squared is k over m. So omega is square root of k over m, and frequency, we know that it is omega divided by 2 pi. So it's 1 over 2 pi square root of k over m. They're not asking about the time period, but the time period is 1 over frequency. So it's 2 pi square root of m over k. It's a very important metric, but we will focus on the frequency now. Frequency is 1 over 2 pi k over m. So basically what we need to know, so the mass doesn't change, but the spring constant does. So if we take a rubber band and cut it in half, the spring constant, as a matter of fact, it doubles. So we have two springs, each has a spring constant of 2k. 2k. How does that work? Why does when cutting a spring in half produces two springs with double spring constant. So how does that work? Well, let's say we have a spring constant K. If we cut it in half, we get two shorter springs, and each has a spring constant of 2k. I can prove that, of course. And imagine we have a chord, and the Young modulus is y. Y is the Young's modulus. And we know that the force, the length of the chord is L. Length of the chord is L. So we know this, the Hooke's law is that the stress is equal to the Young's modulus multiplied by the strain. But stress is force divided by cross-sectional area and equals to the Young's modulus multiplied by the extension, so x divided by original length. Now divide both sides by x and multiply both sides by a. So we get f over x is equal to y multiplied by a divided by L. But f over x is the spring constant, but k is f over x. So the spring constant is this Young's modulus multiplied by the cross-sectional area divided by the length of the rope. So cutting the rope in half, so k is inversely proportional to length. So halving the length will double spring constant, and vice versa. Doubling the length halves the spring constant. Okay, so inversely proportional to the length. So if L is replaced with L over 2, K is YA divided by L over 2, which is 2YA divided by L, which is 2 times the original K. K1 is 2K. Cool. So, and we know from the previous assignment that two springs in parallel will have a combined effect of the spring constant. So total stiffness is 4K. And we know that the frequency is proportional to the square root of K from here. And if it's proportional to the square root of K, so we replace K with 4K, it doubles. So the answer, frequency, doubles. Okay. Let's see if we can demonstrate that. FET. Okay. Um, the problem is I don't know what small is. Yeah, unfortunately, there's no numbers attached to it. Yeah, it's not very useful, but you can clearly see that with a larger spring constant, the mass moves faster. The frequency is higher, of course. Now, one more interesting thing I wanted to show you is this. So if you have two pendulums and one, let's say they both have the same length, one is 1.5 kilograms and the other is 0.1 kilograms. So is the red one is much lighter. Let's let them go. 30 degrees. They have exactly the same time period. Even though they have very different mass, they have exactly the same time period. It's just they have a slightly different phase just because I didn't release them at the same position. That's by the way, that's what phase is. Let's increase the mass and let's reduce the masses. So they have a slightly different phase. So now they are in antiphase. They have a phase difference of pi. Now they have a phase difference of about pi over 2. And now minus pi over 2. So now the blue one is behind the red one. Now, like blue one is tracing the red one. And in the previous one, we had, now the red one is chasing the blue one. So that's a phase difference of pi over 2. And now they have a phase difference of 0. They have the same phase. So hopefully that answers the question what phase is. It's a difficult concept. I'll stop here. Thank you for being patient with me, despite the fact that I've messed up the beginning of the session completely. I hope that was enjoyable. I hope that was useful, and I'll see you all. Oh, yes, I have to say that next week, unfortunately, I'm not available. I'll do the session the week after. So there's no session next week. There's a session in 2 weeks from now. So that would be of course, the 20th, I think, 20th of January. Okay, see you all. Okay, bye.